We know that there are 5 quantities that are associated with the motion of an object, that are position, time, displacement, velocity, and acceleration. Knowing these quantities, it would be possible to describe the motion of an object with a constant acceleration along the straight line. To do so, we will use a set of equations known as equations of kinematics. These equations will provide a very convenient way to determine certain aspects of the motion. Before we learn about this equation, let's agree on the notations. Usually motion has initial position and final position, initial time or final. When the object is moving, it goes from one place to another place. So if we consider the quantities at the initial position, we will assign a subscript node or I to the position, like either it will be x node or x initial. Different texts use different notations, and we are going to use both of them depending on the situation. For the final position, we will assign no subscript, like just an x, we will mean that's the final position, or x final. Similarly, we could do a set of t naught as an initial time, or t initial, t as a final time, or t final. So here, elapsed time, we can use delta t equals t final minus t initial, or we can write delta t equals t minus t initial, or t naught. So usually it is very convenient to use t initial to be 0. When it is 0, then your delta t equals just a t. So we will substitute the elapsed time to be t in our equations. So similarly, if we're talking about velocity, then velocity with the subscript naught would be the initial velocity, with no subscript would be the final or velocity, or we could use v initial, v final as a set of notations. Our first equation comes directly from the definition of acceleration, where acceleration, average acceleration, equals v minus v naught over t. In these equations, as is customary, we dispense with the use of symbols overdrawn with the small arrows for displacement, velocity, and acceleration vectors. We will, however, continue to convey the direction of these vectors with plus or minus signs. So let's move on and multiply this equation by time, both sides. Then we will get AT, and I'm dropping the bar from the top of A. We always mean it's an average acceleration. In this course, we will not discuss varying acceleration. So A times t equals v minus v naught. Now let's add a v naught both to the both sides. And then we will get v naught plus at equals v. And flip this around because it's an equation sign. I can write v equals v naught plus at. So this becomes our first equation, first kinematic equation, which includes four of the quantities, initial and final velocities, the time and an acceleration. So if you have three of those, you can find the other two quantities. So this is first equation. So in other words, if you have the initial velocity v naught, you have the acceleration. At any moment of the time, you can find the velocity of the object. Our next equation comes from the definition of average velocity. So let's recall average velocity equals x minus x naught over t minus t naught. If we consider x naught is it's a zero, we could, or delta x minus x naught will be just an x, and a t minus t naught will be t. So then I can write, instead of the average velocity, I could write statistical average. If you have two numbers, let's say 3 and 2, you want to find the average of these two numbers. What you do, you add them up and divide by the 2. If you have like three numbers, 4, 7, 6, what you do, find the average, you do 4 plus 7 plus 6 divided by 3. So now if you have two quantities, v naught and v, you want to find the average. You find the average v equals v naught plus v over 2. So that's statistical average. So let's just, instead of v average, put the v naught plus v over 2. And then I bring the right side down here, equals x over t. So from here, I can find x equals v naught plus v over 2 times t. What I did here, I multiplied both sides of this equation by t. So I can rewrite this in a nicer form. That would be x equals 1/2 v naught plus v over t. So this will become our second equation that relates initial and final velocity, and at time you find a position. You don't have to know the acceleration. Okay, so let's go ahead and then try to derive the second equation, the third equation, which will follow exactly from the second one. Let's rewrite the second equation as x equals 1/2 v plus v naught, v naught plus v, it doesn't really matter, so v naught plus v t, and then substitute the value of v from first equation. Okay, so we're bringing the value, the expression for v into here. Well, in this case, we will have x equals 1/2 v naught plus, I'm going to use a different color here, so equation 1, so we have a v naught plus at and times t. Let's simplify this. So x equals 1/2 v naught plus v naught is a 2 times v naught plus at and t. Now I'm gonna distribute the 1/2 and a t into this parenthesis. I will have 1/2 t times 2 v naught plus 1/2 t at. Okay, so this 2 and 2 will cancel out. I will have x equals v naught t plus 1/2 a t squared. And this will be my third equation. And finally, for the last equation, we start again from the second one. So x equals 1/2 v naught plus v times t, and this time we substitute the t into it. So we need to do a little bit side work here. If we look at the first equation, maybe even if we look at the definition of acceleration, we can find the time from there. So let me rewrite it in here. So that is acceleration equals v minus v naught over t. From here I can find t equals v minus v naught over a. So then I can plug this one into my second equation instead of t, and let's see what happens. X equals 1/2 v naught plus v times v minus v naught over a. I'm sorry, over a. Now let's recall something from algebra. When we have a minus b times a plus b, this equals a squared plus, minus b squared. So you can check this if you don't remember this identity. You can check it by doing the FOIL here, between multiplying these two parentheses with each other, or you just can't trust me. Now in my case, I have v naught plus v minus v naught. So I can say, I can put it in this way, v minus v naught or v plus v naught. Obviously, I moved the v and v naught in a plus, it doesn't change. So this would become v squared minus v naught squared. So I'm going to substitute this whole thing multiplied together with the v squared v squared minus v naught squared over 2a, and that equals x. From here I can say multiply both sides by 2a. Then I have 2ax equals v squared minus v naught squared, from where I can find v squared equals v naught squared plus 2ax. And this would be our fourth equation. As you can see in this equation, the time is missing. I'm sorry, it's fourth equation. Now let's make a summary of these four equations and see see some properties or some pattern in these equations. Okay, I'm going to make a chart where I have the four different equations. This is the number of the equation, 1, 2, 3, 4. Sometimes I like to refer the equations by numbers. If you could keep the order the same, it's not important, but if you could keep this the same, we can refer to the equations with their numbers. So first was v equals v naught plus at. Second, it was x equals 1/2 v naught plus vt. And the third one was x equals v naught t plus 1/2 at squared. And then the fourth was v squared equals v naught squared plus 2ax. Now what I want to do, I want to put my quantities up here. So the position or displacement, acceleration, final velocity, initial velocity, and time. So for the first equation, we do not have the displacement in it. As you can see, acceleration is present, velocity is present, initial velocity is present, and time is present. So pretty much if you have three quantities known, you can find the fourth quantity by this equation. In reality, every problem you take, if you have 3 out of these 5 quantities, you can find the other 2 based on all these equations. Now, second equation, you have the x, acceleration is missing. You have initial and final velocities and the time. For the third equation, you do have the displacement, you do have the acceleration, you don't have the final velocity, but the initial velocity and the time. And finally, as you can see, everything is present, but the time is not. So the time is absent, the rest are present. Now, if you want to find, or your problem is asking you to find a displacement, you can use the second, third, or fourth equations depending what is given to you. But the first one is not very useful. If you want to find the time, it seems like, or the time is not given to you. I'm sorry, that's what I meant. If the time is not given to you, the fourth equation is the best one to use. You will see this in action when I do some examples, and more example videos will come next. So stay tuned and watch my next videos.